Chapter 10 Oracles. In this chapter, we address oracles, which are structures that can supply Ethereum smart contracts with external data sources. The word oracle derives from Greek mythology, where it refers to a person in contact with the gods who could see future visions. An oracle is a device in the sense of blockchains which can address questions external to Ethereum. Ideally, oracles are trustless entities, meaning they don't have to be trusted because they run on decentralized principles. Why oracles are needed? A core component of the Ethereum framework is the virtual machine Ethereum, with its capability to implement programs and update the status of Ethereum on any node in the decentralized network, restricted by consensus rules. To maintain consensus, the execution of EVM must be completely deterministic and based solely on the common sense of the state of Ethereum and the signed transactions. This has two especially significant consequences. Firstly, that there can be no inherent source of randomness for the EVM and smart contracts to deal with. Secondly, extrinsic data can only be introduced as the data payload of a transaction. Let's unpack those two results more. In order to understand the prohibition of a true random function in the EVM to provide randomness for smart contracts, think through the consequence on attempts to achieve consensus after performing such a task. Node A would execute the command and store 3 in its storage on behalf of a smart contract, while Node B would store 7 instead, executing the same smart contract. Therefore, nodes A and B, despite having run exactly the same node in the same sense, will come to different conclusions about what the resulting state should be. Indeed, it could be that every time the smart contract is evaluated, a different resulting state would be achieved. As such, the network, with its multitude of nodes operating independently across the world, will have no means of ever finding a decentralized consensus about what the resulting state would be. In reality, it would get much worse quite quickly than this case, as knock-on effects, including ether transfers, would build up exponentially. Note that pseudo-random functions, such as cryptographically protected hash functions, which are deterministic and thus can and are part of the EVM, are not adequate for many applications. Take a betting game that feigns coin flips to settle bet payouts that need to randomize heads or tails. A miner can gain an advantage by playing the game, and only include their transactions in blocks they win for. So how are we going to get around that problem? Well, all nodes should agree on the contents of signed transactions, so that extrinsic information, including randomity sources, price information, weather forecasts, etc., can be added as the data part of transactions sent to the network. These data obviously postpone the issue. We use oracles in the rest of this chapter to try and address these problems, which we'll explore in detail. Oracle use cases and examples. Oracles, preferably, provide a trustless, or at least quasi-trustless way to get extrinsic, i.e., real-world or off-chain details, such as football game results, gold prices, or genuinely random numbers, to the Ethereum blockchain for use in smart contracts. They can also be used to safely transmit data directly to dApp frontends. Hence, oracles can be seen as a tool to fill the gap between the off-chain environment and smart contracts. Allowing intelligent contracts to implement contractual ties based on real-world events and data significantly broadens their reach. It might, however, also add external threats to the security model of Ethereum. Consider contracting for smart will, which distributes assets when an individual dies. This is something that is addressed frequently in the smart contract room, and highlights the dangers of a trusted oracle. If the amount of inheritance managed by such a contract is high enough, then there is a very strong incentive to hack the oracle and cause asset transfer before the owner dies. Remember that certain oracles, such as college certificates or government IDs, contain data that is unique to a particular private source. The source of such data, such as a university or department of government, is completely respected, and the reliability of the data is subjective. Reliability is decided only by an appeal to the source authority. Therefore, these data cannot be provided without trust, i.e., without trusting a source, because there is no independently verifiable objective reality. As such, in our description of what counts as oracles, we include such data sources, as they also offer a data bridge for smart contracts. Generally, the data they include takes the form of attestation, such as passports or achievement records. Attestations will become a major part of the future success of blockchain platforms, particularly with regard to the related issues of identity or reputation verification. So it is important to explore how blockchain platforms can support them. Some more examples of data that could be supplied by oracles include random statistics or entropy from physical bases such as quantum or thermal processes, e.g. choosing a winner equally in a smart lottery contract. Parametric triggers related to natural hazards, e.g. catastrophe bond triggering smart contracts such as earthquake bond Richter scale measurements. Exchange rate data, e.g. for fiat currency accurate pegging of cryptocurrencies. Information on capital markets, e.g. price baskets of tokenized assets or securities. Reference benchmark data, for example, the integration of interest rates into smart financial derivatives. Static, pseudostatic data, identification tags, country codes, currency codes, etc. Time and frequency data, accurate time calculation for event triggers. Weather data, e.g. weather forecast insurance premium calculations. Political events, for business resolution of forecasts. Sporting events, business settlement for betting and sports fantasy contracts. Geolocation data, e.g., as used for monitoring the supply chain. Damage check, for insurance contracts. Other blockchains happening. Interoperability features. Ether market price, e.g., oracles for fiat gas price. Flight statistics, for example, as used by flight ticket pooling groups and clubs. We will discuss some of the ways oracles can be implemented in the following pages, including simple oracle patterns, computational oracles, decentralized oracles, and oracle client implementations in Solidity. Oracle development patterns. All oracles, by design, have some main functions. Those include the ability to obtain data from a source outside the chain, on-chain exchange of data with signed post, make the data available by placing it in storage for a smart contract. Probably, if the data is accessible in the storage of a smart contract, it can be accessed through other smart contracts via message calls, which appeal to a recovery feature of the smart contract of the oracle. It can also be accessed directly by Ethereum nodes or network clients by looking into the storage of the oracle. Starting with the simplest immediate read, oracles are those that provide data that is only needed for an immediate decision, like what is the address for the Ethereum book.info, or is this person over 18? Those wishing to query this kind of data tend to do so on a just-in-time basis. The lookup is done when the information is needed, and possibly never again. Examples of such oracles include those that hold data about or issued by organizations, such as academic certificates, dial codes, institutional memberships, airport identifiers, self-sovereign IDs, etc. This type of oracle stores data once it is in its contract storage, whence any other smart contract can look it up using a request call to the oracle contract. It may be updated. The data in the oracle storage is also available for direct lookup by blockchain enabled, i.e., Ethereum client connected applications without having to go through the palaver and incurring the gas costs of issuing a transaction. A shop wanting to check the edge of a customer wishing to purchase alcohol could use an oracle in this way. This type of oracle is attractive to an organization or company that might otherwise have to run and maintain servers to answer such data requests. Note that the data stored by the oracle is likely not to be the raw data that the oracle is serving, e.g., for efficiency or privacy reasons. A university might set up an oracle for the certificates of academic achievement of past students. However, storing the full details of the certificates, which could run to pages of courses taken and grades achieved, would be excessive. Instead, a hash of the certificate is sufficient. Likewise, a government might wish to put citizen IDs onto the Ethereum platform, where clearly the details included need to be kept private. Again, hashing the data more carefully in Merkle trees with salts, and only storing the root hash in the smart contract storage would be an efficient way to organize such a service. The next configuration is publish to subscribe, where an oracle that essentially provides a data transmission service that is supposed to adjust, maybe both periodically and frequently, is either challenged by an on-chain smart contract or monitored for changes by an off-chain daemon. This category has a structure similar to RSS feeds, WebSub, and the like, where the oracle is restructured with fresh information and a flag indicates that new data is accessible to those who find themselves to be subscribed. Interested parties will either survey the oracle to verify if the latest information has changed, or listen to changes to the oracle contracts and respond when they occur. Examples include price updates, information about the environment, economic or social indicators, traffic data, etc. In the environment of web servers, polling is rather slow, but not so in the peer-to-peer sense of blockchain platforms. Polling for data changes is a local call to a synced client. Ethereum event logs make it especially easy for applications to search for oracle updates, and even this pattern can be called a drive service in certain respects. Nevertheless, if polling is performed from a smart contract, which may be appropriate for certain decentralized applications, e.g., where activation opportunities are not possible, then there may be substantial gas expenditure. The request to response group is the most complicated. This is when the data space is too big to be processed in a smart contract, and users are required to use only a small part of the total dataset at a time. It is also a standard applicable service provider enterprises. Practically speaking, such an oracle could be implemented as a network of smart on-chain contracts and off-chain infrastructure used to track requests and to get and return data. A demand for data from a decentralized application will usually be an asynchronous process with multiple steps involved. Firstly, an EO transacts in this pattern with a decentralized application, resulting in an interaction with a function specified in the smart oracle contract. This feature initiates the request to the oracle with the relevant arguments outlining the requested details, as well as additional information which may include a callback function and scheduling parameters. If this transaction has been authenticated, the request for an oracle can be detected as an EVM event generated by the oracle contract. Or as a change of state, the arguments can be retrieved and used to execute the actual query of the data source off-chain. The oracle can also require payment for request processing, gas payment for callback and permission to access the data requested. Finally, the consequential data is being signed by the owner of the oracle, attesting to the validity of the data at a particular time, and transmitted in a transaction to the decentralized application making the request, either directly or via the oracle contract. The oracle broadcasts more transactions, updating the data at regular intervals, depending on the scheduling parameters, e.g., end-of-day pricing information. The steps for an oracle of request answer can be summarized as 1. Receive a question through a dApp. 2. Parse the problem. 3. Check that authorizations for payment and access to data are given. 4. Retrieve relevant data from a source outside the chain and encrypt it if necessary. 5. Sign into the transactions with the included info. 6. The transactions are transmitted to the network. 7. Schedule any more transactions possible, such as updates, etc. A number of other methods are also possible. For example, data can be obtained directly from and returned by an EOA, removing the need for a smart Oracle contract. Similarly, question and answer could be made to and from a hardware sensor allowed by the Internet of Things. The oracles may either be individual, software, or hardware. In client-server architectures, the request-response pattern mentioned here is commonly seen. Although this is a useful message pattern and allows for two-way communication between applications, it may be inappropriate under some circumstances. For example, under a request-response model, a smart bond needing an Oracle interest rate would have to request that data on a regular basis to ensure the rate is always right. Since interest rates rarely alter, a publish-subscribe pattern here may be more appropriate, especially when taking into account the limited bandwidth of Ethereum. Publish-subscribe is a trend in which publishers, in this case oracles, do not explicitly send messages to recipients, but rather categorize published messages into different groups. Subscribers may express an interest in one or more classes and then download certain messages of interest. Under such a model, an oracle might write the rate of interest to its own internal storage anytime it changes. This can be read from the oracle contract by several subscribed dApps, thus reducing the effect on network bandwidth while lowering storage costs. In a broadcast or multicast system, an oracle would post all messages to a channel, and under different subscription modes, subscription contracts will listen to the channel. For instance, an oracle might distribute messages to an exchange rate channel for the cryptocurrency. A subscribing smart contract might request the channel's full output if it needed the time series for example, a moving average measurement. Another would demand only the latest rate for a measurement of spot prices. A broadcast pattern is acceptable where the oracle does not have to learn the signing contract's identity. Data authentication. If we presume that the data source being acquired by a dApp is both authoritative and trustworthy, not a significant assumption, an outstanding question remains. Given that separate entities can run the oracle and the request-response process, how can we trust that mechanism? There is a distinct possibility that in-transit data may be manipulated. So, it is important that option approaches may testify to the validity of the returned data. Two common data authentication approaches are authenticity proofs and trustworthy execution environments, TEAs. Proofs of authenticity are cryptographic assurances that the data was not changed. We essentially transfer the trust from the data carrier to the certifier, the issuer of the certification. Based on a variety of attestation methods, e.g. digitally signed proofs, through verifying on-chain proof of authenticity, smart contracts will verify data validity before operating on it. Oracleize is an illusion of an oracle service that leverages various proofs of authenticity. TLS and notary proofs require a client to provide evidence that HTTPS web traffic between a client and a server acquired to a third party. While HTTPS itself is secure, it does not support the signing of data. Consequently, TLS and notary proofs depend on TLS and notary signatures via page signers. TLS notary proofs exploit the transport layer security TLS protocol, allowing the TLS master key, which signatures the data after assessing it, to be split into three parts: the server, Oracle, the auditee, Oracleize, and the auditor. As an auditor, Oracleize uses a virtual machine instance of Amazon Web Services, AWS, which can be checked as unmodified after instantation. This AWS instance stores the TLS notary secret so it can provide evidence of integrity. While it provides higher guarantees against data manipulation than a mere request-response process, This approach requires the presumption that Amazon will not exploit the VM instance itself. Town Crier is an authenticized T-based data feed Oracle system. These methods use hardware-based protected enclaves to ensure data integrity. Town Crier uses Intel's Extension Security Guard, SGX, to ensure that answers from API queries can be checked as authentic. SGX offers guarantees of fairness, ensuring that applications running in an enclave are secured by the CPU from any other mechanism being tampered with. It also provides secrecy, ensuring that the state of an application while operating inside the enclave is inaccessible to other processes. And finally, by producing a digitally signed proof that an application securely marked by a hash of its creation actually runs within an enclave, SGX makes attestation. By checking this digital signature, a decentralized application will prove that a Town Crier instance runs securely within an SGX enclave. This, in effect, shows that the instance was not tampered with, and therefore the data generated by Town Crier is authentic. Additionally, the confidentiality property allows Town Crier to handle private data by allowing to encrypt data queries using the public key of the Town Crier case. Operating the query response process of an oracle inside an enclave such as SGX essentially allows one to think of it as running safely on trusted third-party hardware, ensuring that the requested data is returned untampered, assuming we trust Intel and SGX. Computation oracles. We have so far only addressed oracles in the sense of requesting and supplying data. Nevertheless, oracles can also be used to perform arbitrary computation, a function which can be particularly useful given the inherent block gas limit of Ethereum and comparatively expensive cost of computation. Rather than simply relying on the results of a query, it is possible to use computational oracles to carry out computation on a set of inputs and return a measured result that would have been infeasible to calculate on-chain. For example, to estimate the yield of a bond contract, one might use a computational oracle to perform a computationally intensive regression calculation. If you want to trust a centralized but auditable service, you can go to Oracleize again. They provide a service that allows for decentralized applications to request a computation output performed on a virtual machine with Sandbox's AWS. The AWS instance generates an executable container from a user-configured Docker file packed in an archive uploaded to the Interplanetary File System, IPFS. On demand, Oracleize recovers this archive using its hash and then initializes and executes the Docker container on AWS, passing any arguments as environment variables to the program. The containerized application carries out the calculation subject to a limit and writes the result to standard output, where Oracleize will retrieve it and return it to the decentralized application. Oracleize at this time proposes the service as an auditable T2 micro AWS case, so it is possible to check that the appropriate Docker container has been executed if the computation is of some non-trivial nature. This is not a completely decentralized solution, however. Conclusions. As you can see, Oracleize provides the smart contracts with a vital service. They add external evidence to the execution of contracts. In that, of course, oracles often pose a huge risk if they are trusted sources and can be manipulated. The smart contracts they feed can be manipulated. In general, be very conscious about the trust model when contemplating the use of an oracle. If you believe the oracle can be trusted, exposing it to potentially false inputs can compromise the security of your smart contract. This being said, oracles can be very useful when proper attention is given to the security assumptions. Decentralized oracles will answer some of those issues and deliver trustless external data to Ethereum smart contracts. Choose carefully and start exploring the connection between Ethereum and the true world provided by oracles. When part of Microsoft's broader escape system, the definition of a cryptlet when standard for verifiable oracles truths has been formalized. Cryptlets run inside an encrypted capsule that abstracts the network, such as input and output, and has the crypto delegate attached in such a way that incoming and outgoing messages are automatically signed, authenticized, and proven. Cryptlets back dispersed transactions so that contract logic can take on complex multi-stage, multi-blockchain, and ACID transactions of external systems. This helps developers to build truth settlements that are portable, isolated, and private for use in smart contracts.